Analyzing what happened yesterday is no longer sufficient. Modern business baseline dictates that systems must predict and respond to events precisely as they occur. To achieve this, engineering teams must seamlessly merge two distinct and massive domains: distributed stream processing and live machine learning inference. Architecting this creates a strict engineering tension. The system is required to execute complex calculations with single-digit millisecond latency, while simultaneously absorbing unpredictable, massive scale. Operating at this speed and scale introduces secondary constraints. The pipeline must maintain strict fault tolerance and remain cost-efficient, even during sudden bursts of traffic or component failures. This diagram outlines the solution framework, a scalable, strictly sequenced four-layer architecture, specifically designed for deployment in an AWS environment. We will forensically construct this blueprint from left to right, evaluating the technical trade-offs required at each architectural boundary. Real-time intelligence requires a foundational architectural commitment that begins with how raw data is initially captured. Raw data from IoT sensors, mobile apps, and system logs rarely arrives in a predictable flow. It hits the system in highly volatile, massive bursts. Routing these massive traffic spikes directly into a processing engine immediately overwhelms compute capacity, leading to catastrophic failure and data loss. Layer 1 solves this by placing a durable write-ahead log, like Amazon Kinesis data streams or Apache Kafka, at the front of the architecture. This log acts as a durable buffer, writing incoming events safely to disk, holding them until the downstream system can consume them. Engineers must defend their technology choice here based on throughput needs. Amazon Kinesis provides fully managed simplicity and tight AWS integration. Kafka, often deployed via Amazon MSK, offers advanced partitioning control and superior long-term cost scaling for absolute massive workloads. Layer 1's true purpose is structural decoupling. It isolates the volatility of the real world from the logic of the compute engine. Once safely buffered, raw events are useless to a machine learning model. They require immediate transformation. This introduces Layer 2, the stream processor. For this precise architectural node, AWS Managed Service for Apache Flink is the standard engine. Flink provides the critical capability of stateful stream processing. By retaining memory of past events, it calculates complex, windowed metrics continuously on the fly. For example, if a specific sensor ID transmits a single new reading, Flink instantly queries its state to compute a rolling 5-minute temperature average for that exact device. An architectural gap still remains. Flink only evaluates the live stream. It is blind to the historical context required to build a complete machine learning feature vector. If an event contains a specific user ID, the model must evaluate that user's lifetime spending history, data that does not exist inside the live event packet. To resolve this context gap, we deploy an online feature store. Using an ultra-low latency NoSQL database like Amazon DynamoDB is mandatory here. It allows Flink to fetch external historical context in single-digit milliseconds without stalling the live pipeline. The Flink engine merges the live event data with the DynamoDB context, outputting a fully constructed feature vector. Layer 2 takes a chaotic stream of isolated inputs and transforms it into structured, context-rich intelligence, preparing it for inference. Layer 3 is the central bottleneck of the blueprint. With the feature vector complete, the system must execute the machine learning prediction. This forces a distinct architectural dilemma. Where exactly should the machine learning model physically reside in relation to the stream processor? Approach A is embedded or inline scoring. The model is loaded directly into the Flink application code. Because the data never leaves the processor's memory, there is zero network I/O, providing the absolute minimum computational latency. The operational cost of this speed is severe. Updating the model requires tearing down and redeploying the entire streaming pipeline, destroying deployment agility. Approach B utilizes external RPC or API calls. The model is extracted and placed into its own dedicated inference service. This introduces network distance. This provides a clean separation of concerns. Models can be updated, swapped, or scaled instantly without touching the fragile streaming infrastructure. The resulting penalty is network distance. Crossing the network introduces I/O latency, risking the strict real-time service level agreements. To mitigate this network penalty at massive scale, AWS provides two distinct solutions. The first is Amazon SageMaker serverless inference. Because SageMaker fully manages the underlying infrastructure and handles automatic scaling, it is the ideal choice for environments experiencing highly unpredictable, spiky traffic. The second solution targets ultra-strict latency requirements, deploying Amazon EKS with the Onyx runtime. By exporting models to the highly efficient Onyx format within Kubernetes, engineers gain exact control over lightning-fast gRPC communication, outperforming standard HTTP. There is no perfect choice at Layer 3. Engineers must explicitly choose to sacrifice either absolute computational speed or long-term deployment agility based on the specific business use case. Generating a highly accurate prediction, such as a 98% probability fraud score, has zero business value if it remains trapped inside the processing layer. Layer 4 solves this via the fan-out pattern. The final prediction exits the inference layer and instantly splits into multiple parallel pathways. Pathway 1 dictates immediate action. Critical alerts are routed directly to Amazon SNS, triggering instantaneous notifications to end users or automated security systems. Pathway 2 handles asynchronous queuing. The data flows to Amazon SQS, neatly lining up follow-up tasks for secondary systems or manual human review. Pathway 3 secures long-term storage. The exact same prediction, alongside its original input, streams through Kinesis Data Firehose directly into an Amazon S3 data lake. This final layer ensures that a single millisecond calculation triggers simultaneous, highly specialized workflows across the entire enterprise architecture without ever blocking the upstream processing stream. Wiring these components together merely establishes the baseline. Operating this architecture at scale requires ruthless optimization. Engineers constantly navigate the central axis of streaming data systems, balancing latency, measured in milliseconds, against throughput, measured in events per second. When raw throughput takes priority, teams deploy a technique known as microbatching. By intentionally belaying a request by just 5 milliseconds at Layer 3 to group 10 distinct events into a single batch call, the system significantly multiplies overall throughput capacity. Beyond execution speed, the architecture must survive infrastructure failures. This dictates multi-availability zone replication for both Kinesis and Kafka clusters to eliminate single points of failure. Simultaneously, Flink utilizes a built-in checkpointing mechanism. By taking periodic snapshots, it guarantees exactly one's processing, recovering from the exact millisecond of failure. In the physical world, machine learning models inherently degrade. Human behavior shifts, environments change, and input data evolves. This graph illustrates model drift monitoring. Over time, a gap forms between the model's predicted outputs and the actual real-world results. The Layer 4 S3 data lake continuously compares the original inputs against these actual outcomes. When the accuracy inevitably drops below acceptable thresholds, the system automatically triggers a retraining cycle. High-performance real-time ML is achieved through the rigorous orchestration of isolated data buffers, stateful memory management, and highly optimized network routing.